Now that we know how stockpiles are made and the safe and proper ways to acquire representative samples, we are ready to identify our sample, transport it to the lab, and reduce the field sample for testing. This next segment will cover these topics. We will begin with a video demonstrating proper sample reduction procedures for fine and coarse aggregates.
Method A is the mechanical splitter, which can be used for coarse aggregate and for fine aggregate that is drier than the saturated surface dry condition. Method B is quartering using a shovel or scoop, which can be used for coarse aggregate or for fine aggregate with free surface moisture. Method C is called miniature stockpile sampling. Method C can be used for either type of aggregate. For fine aggregate, there are specific requirements determined by the moisture content. As a rule of thumb, if the fine aggregate will retain its shape when you mold it in your hand, you may consider it wetter than saturated surface dry. Samples of fine aggregate that are drier than saturated surface dry may be reduced with a mechanical splitter using Method A. Samples of fine aggregate that have free surface moisture may be reduced by quartering using Method B. Drying the entire sample at temperatures that are less than those for any specified tests, and reduce with a mechanical splitter or cone splitter using Method A. Or, if the field sample is very large, you may make a preliminary reduction using a mechanical splitter that has chute openings that are wider than 1.5 inches. That preliminary reduced sample can then be dried and further reduced using Method A. Or, treating the entire sample as a miniature stockpile using Method C. We'll begin by reviewing mechanical splitters and Method A. A typical mechanical splitter for coarse aggregate is shown here. The technician is changing the movable bars to a wider chute spacing. The splitter must have an even number of equal width chutes. It must have at least 8 chutes for coarse aggregate and at least 12 for fine aggregate. Each chute should be approximately 50% wider than the largest particles in the sample that is to be split. Splitters are equipped with 2 pans that catch the 2 halves of the sample once it's been split. This splitter has a hopper that holds the initial charge, and by operation of the lever, the sample can be fed to the chutes in a controlled manner. Let's continue with a discussion of Method A for reducing a sample of coarse aggregate or dry fine aggregate. Begin the process by weighing the field sample, having tared the weight of the sample containers. Take the sample containers and empty them into the hopper of the splitter as shown in this sequence. Level the sample out in the hopper so that approximately equal amounts flow through each chute. Ensure that the hopper is empty and that the chutes are clear. In this example, the technician is using 5-gallon buckets for the half that he will resplit and a wheelbarrow for the half that he will discard. Once the original sample has been split, take the retained half and reduce it further to test sample size. In this sequence, 1.5 buckets are half of the original field sample. All of the half sample retained is poured into the hopper. At this point, 1/2 of this split is discarded and half retained. The retained half is then returned directly to the hopper for the final split. The final split for testing should then be weighed to verify that it's sufficient for the tests that are required. The second half of the sample may be discarded. If split samples are required, the second half of the final split should be used. It is important that each sample be fully identified through a tag securely fixed with the sample. Required sample identification includes sample number for the week of the year, the pit number or facility that was sampled, the type of sample such as stockpile or belt sample, process sample, sampler, grade of material, and date sampled. Now let's review using a smaller mechanical splitter for dry, fine aggregate. In this example, we have a splitter that does not have a hopper, so the technician uses a pan that is the same length as the splitter. Notice that he pours in approximately half from one side of the splitter and half from the other side. Pour the sample into the splitter in a controlled manner to allow smooth flow into the chutes. It's important to ensure that the chutes are clean after each split. The final split is placed in a weighing pan and a brush used to ensure recovery of all of the fines. The cone splitter may also be used. The aggregate is poured over an X-shaped splitter located at the bottom of the cone. The gate is opened, allowing the quartered aggregate to spill into 4 buckets. Recombining buckets from opposite sides of the splitter, continue quartering to obtain the proper test sample size. Method B uses quartering of the sample until 1/4 of the material equals the testing size required. You will review 3 quartering methods: quartering coarse aggregate with a shovel, quartering fine aggregate on a bench top, stick and blanket method. Let's begin by reviewing quartering coarse aggregate with a shovel on a clean, level, and smooth surface. The surface should allow only minimum loss of the sample during the quartering process. Wash the surface to remove dust, aggregate, and other contamination. Remove excess surface water if the sample is for testing -200 content. Place the material on the clean surface. Using a shovel, mix the material thoroughly by turning the entire sample over 3 times. With the last turning, shovel the entire sample into a conical pile by placing each shovelful on top of the previous shovelful. Flatten the resulting cone-shaped pile to a uniform thickness and diameter by pressing down on the top of the cone with the shovel or other suitable device. Divide the flattened pile into 4 approximately equal quarters by splitting along 2 perpendicular diameters with the shovel, a trowel, or other suitable device. Carefully separate the 4 quarters from each other. Ensure that material from one quarter does not get included with another. Remove 2 opposite quarters using the shovel, including fine material. Scrape the cleared spaces clean. Remix the remaining 2 opposite quarters and continue to quarter the remaining pile until the sample has been reduced to the required size. A variation of this procedure can be used for damp fine aggregate on a bench top. As shown here, dump the sample on the bench top and mix well using your hands or a trowel. Once the sample has been adequately mixed, flatten the pile and divide it into 4 approximately equal quarters. Remove 2 opposite quarters, including the fines, and remix the remaining 2 opposite quarters. Continue to quarter until the sample has been reduced to the required size. The stick and blanket method is used where other equipment isn't available and the working surface is uneven. Place the material on canvas or another durable fabric. Mix the sample by lifting alternate corners of the blanket. Flatten the pile. Insert a round-ended stick or pipe under the blanket at the center of the pile. Lift the stick to separate the sample into 2 approximately equal piles. Reinsert the stick under the blanket at the centers of the 2 piles at right angles to the first division. Again, lift the stick to separate the material into 4 approximately equal piles. After removing opposite quarters and remixing the remaining quarters, continue this procedure until the material has been reduced to the size required. The third method of sampling is the miniature stockpile. You begin this reduction method by placing the field sample on a clean blanket of canvas or other suitable material. Thoroughly mix the sample and form it into a miniature stockpile. Take the sample by selecting a minimum of 5 equal-sized increments from random locations on the miniature stockpile. You may take the samples with a small sample tube, a small scoop, or a spoon. In order for reproducible and consistent test results to be obtained, standard methods of sampling and splitting must be followed. The producer evaluates his production using the test results and statistical control methods. If the samples are collected using incorrect, non-standard methods, as shown here, the statistical analyses will not be valid. Samples collected at different times using non-standard methods will not be comparable.